Domains. We're going to look now at how we find domains of functions. And what I mean by that, let's consider this function right here, f of x equals 1 over x. If I ask you, just find the natural domain of that function, what I'm asking is, what values can x take on? Because x is the independent variable. Are there any values that I can't plug into this function? Can x equal anything that if I try to plug that value into the function, I get something that's undefined? I'm going to call this case 1, where we have a variable, an independent variable in the denominator. Well, let's look here. I can certainly plug in a 5. F of 5 is 1/5. No worries there. So that, 5 works. 5 is, in other words, 5 is part of the domain of this function. Well, I can plug in -5 also. So -5 is part of the domain. 2, I get 1/2. That's part of the domain. 1/10. Yeah, 1 divided by 1/10 is 10. Good. But 0. 1 over 0 is undefined. So what this tells me is 0 is not part of the acceptable values for x. And what I have to do is I have to say, okay, the domain is not going to include 0 in it. Now, it can be anything else. All other real numbers. You could plug in any real number in for x here and you would be fine, but not 0. That's the one exclusion. So here's the situation. When we face a function that has an independent variable in the denominator, what we have to do is we have to figure out what values will make that denominator 0. In other words, what values for x, the independent variable, will make the denominator 0. And when we find those values, we have to exclude them. Now let's look at case 2. Let's suppose we have an even indexed radical. Here, the square root. When I say even indexed, I mean like the square root, the 4th root, the 6th root, the 8th root. This is not pertaining to cube roots or 5th roots. It's only even indexed radicals. When we have these, we have a different concern than we did with the 1 over x. So let's look at this. Certainly 16 is part of the domain because f of 16, square root of 16 is 4. So yeah, 16 is definitely part of the domain. Okay, 9, that's also part of the domain because the square root of 9 is 3. 4, that's part of the domain. 0, yeah, even 0. The square root of 0 is 0 because 0 squared is 0. But -1. These are real functions. F of x equals the square root of x. We're assuming this to be a real function, meaning you get real outputs. So we're going to exclude all these numbers that will give us imaginary components. So -1, -4, -3, all those negative numbers. So whenever we have a situation like this, that's our concern. What's going to make the radicand less than 0? And we have to find out what values for x will make the radicand greater than or equal to 0, and that is our domain. So let's look at some examples here. Let's suppose we have this function here. F of x equals 3 over 2x plus 1. The way we proceed to find the domain is set the denominator equal to 0 and solve it. So we did some investigating here. We said, what's going to make that denominator 0? So I did that. I solved the equation, and I found, there it is. X equals -1/2. We can't ever let x be -1/2. So we could state the domain this way. X can't be -1/2. X is not equal to -1/2. That means all other real numbers are acceptable except that one. Now, I could write that in interval notation this way. -infinity to -1/2. Notice not including -1/2. Jump over it, come out on the other side, -1/2 to infinity. This is the domain. This is the interval notation form. Okay, let's look at another one. F of x equals x over x squared minus 5x minus 6. Going to set the denominator equal to 0 do some investigating. Let's find out what will make that equal to 0. So I solve it by factoring. And I find that if x is equal to -1 or if x is equal to 6, either one of those will make this denominator 0. So we could say, okay, our domain is x can't be -1 and x can't be 6. It can't be either one of those things, either one of those values. Or I could write it in interval notation. -∞ to -1. Jump over that. -1 to 6. Jump over that. 6 to infinity. In other words, x can be in any of these intervals here. It just can't be -1 or 6. And this is the way we can write it in interval notation. Okay? Let's suppose we've got the square root of 2x plus 1. Okay, now this is the case too, where we're going to take the 2x plus 1, set it greater than or equal to 0. So here we have, okay, x has to be greater than or equal to -1/2 if we want the 2x plus 1 to be greater than or equal to 0. So we could write that in interval notation this way. Okay, let's look at this one. Here's the fourth root. Now, by the way, if this had been the cube root, we would just say the domain is all real numbers. So if this had been the cube root of 1 minus 2x, all real numbers. We're just looking at these two cases where we have to worry about the domain. Now, as we go about our studies, as we progress through our studies, we'll find other cases where we have to worry about domains. But right now, we're just looking at these two cases. So notice we take 1 minus 2x greater than or equal to 0. If I move the -1 to the other side and then divide by -2, remember, you have to flip the inequality symbol, right? When you divide or multiply by negative in an inequality, you flip the direction of the inequality. So here's the domain on that one. Okay? So we've looked at an example of case 1 and an example of case 2. Now let's look at a combination of it, case 1 and case 2, because notice in the top we have this square root. So 2x plus 1 has to be greater than or equal to 0. And at the same time, x minus 1 can't be equal to 0. Now that means that x has to be greater than or equal to -1/2, and x can't be 1. So here's what we have. X is going from -1/2 to 1, but it has to take a pause, jump over 1, and then 1 to infinity. So there is how we can find the domain when we have a combination. You have to be a little bit more circumspect. And it's not, you have to analyze, okay, what's going on here? I mean, and it takes a little bit more time and effort, but that's how we find the domain.